Last Friday, you spent the past 2 days writing codes and writing tests. And you're very happy because it's the end of the day, you've done all the tests pass, and the cherry on the cake, you have this 100% test coverage, this metric that you love. So you're happy, you go on a weekend, you think that, okay, I can enjoy my weekend, everything works, and you go on weekend. But then Monday happens. You go back to the office, still proud of yourself, like I did a good job last week, but then something happens. You have tons of emails, Jira tickets, GitHub issues, because there's bugs in your code. And then you wonder, what happened? What did I miss? What did I do wrong? I mean, I did all the tests, all of them passed. I have 100% test coverage, so everything should be nice. Well, just a bit of history before we start about testing. So I assume back in the day, when you had small pieces of code, testing a software wasn't that complicated. You just write your code, compile, run it, just try the few functions, and then you see if it works. Well, that worked before. That can maybe still work for side projects, for very tiny projects. But for very big projects, when you have more classes, functions, files, that doesn't work. You can't just say, okay, I compile, I test. If all my manual test works, it's okay. No, you can't do that. So at some point, people came with this test framework, like PyTest, like Jasmine in JavaScript. So all these test frameworks that made the life easier for developers to test their softwares. And these software introduced this so-called test coverage. And basically a test coverage, when you have 100%, what it means that every single line of your code is run by the test suite. Doesn't mean it's tests properly, but the tests go through all the lines. But the question is, does 100% test coverage mean 100% of your code is tested? Well, if you're here, it's because the answer is not necessarily. Doesn't mean that your the tests go through all the lines, that everything has been tested. So hi everyone, my name is Olivier. I'm a developer advocate at AWS, and I'm with...
Hi everyone, my name is Maha. I am engineering manager at Elastic, and I'm leading a team, the release engineering team at Elastic. With this team, we are providing the other products teams at Elastic with frameworks, tool guidance on how they can produce their reusable artifacts. I also have a PhD in optimizing performance of multi-tier distributed system deployed in a private cloud. And today we're gonna talk about mutation testing. What is it? How can we benefit from it? And how can we really optimize our test suite? So let's start answering the first question. What's a mutation testing? Mutation testing is a technique where it allows us to evaluate the efficiency and the effectiveness of our test suite. What does that mean? And how can we do that? So we would like to be able to measure the ability of our test suite in detecting small fault, artificial faults, seeded systematically into our program. And those faults, we call them mutants. We're gonna talk about them in the coming slides. So if our test suite was able to detect those small faults that we inject artificially in our system, this means that our test suite is efficient. Otherwise, it's not sufficient, which means that it's missing some use cases. There are some edge cases not covered by this test suite. Historically speaking, the first time this concept appeared was by a student named Richard Lipton in 1971. However, the first implementation appeared as a PhD work of a student at Yale University in the 1980s. So the idea, as Olivier said, is to say, does 100% code coverage is enough, this metrics to say that our code is doing what's supposed to do and our test suite is able to detect any edge cases in our code. That's why this concept has been introduced. So the idea or the benefit from introducing this concept, as I said, we would like really to measure the effectiveness and the sufficiency of our test suite. And in this order, when this mutation test will report us statistics about what has been tested in this test suite, we will be able really to indicate those missing use cases, edge cases that they are not covered by this test suite. So we will be able to improve our existing test suite. And last but not least, this mutation testing will help us to pinpoint any root cause of any regression in our test suite. So I have said plenty of concepts now at the same time. Let's break those into smaller chunks. So the question now, how can we use mutation testing? So I said that we would like to introduce faults, small faults, and inject them into our initial program, and then run the test suite against those modifications, small modification. Keep in mind, if the test suite passes those modifications, this means that our test suite is weak. So we need the test to fail those modifications. Meaning, failing means that the test suite was able to detect that there is modification has been introduced into the initial program.
If you get lost, don't worry, we have samples after.
Yes. So those modifications, I keep talking about those small modifications and those small artificial faults introduced or seeded into the system. Those modifications, we call them mutants. So what is a mutant? A mutant, it's a change copy of our program where we introduce only one change at a time. Okay? And then we run the relevant test suite against that modification, and we see if the test fails, this is good, which means that the test was able to detect this modification I just introduced. Otherwise, if it passed, it means that the test didn't detect any modification, and this means that my test suite is not sufficient because it wasn't able to detect this modification, meaning that there is something missing I need to add, I need to improve my test suite. Okay, let's have an example on a mutant. How can we create a mutant? So what I said, like a modified copy of the initial program. So here, it's a small function in Python. How many of you develop some Python? Okay, cool, great. There are plenty, great. So here's a small function in Python where I compute the square root of a number. So when I get the number, I check if the number is smaller than 0. I raise an error. Otherwise, I return the square root of that number. I write the test for this function. And so the test, there is an assertion statement saying, okay, the square root of 49 equals to 7. So if I run this test will pass and everything is fine. We agree, right? There is nothing special here. So I want to make sure if this test is enough or not. So what I'm going to do, I'm going to create a mutant by making small modification in the initial function. And one modification at a time. Remember, it's only one. So I'm going to pick the operation, the comparison smaller, and I'm going to change it to smaller or equal. Okay? And then I will rerun the test against this modification. So when I run it, actually, the test will pass, meaning that the mutant survived. So our goal in mutation testing is to kill the mutants, meaning that the test should fail all those changes, detect all those changes. So this means that my test suite wasn't enough. There was something missing, okay? Because the test didn't detect this change I just introduced in the code. So the mutant survived, and this is not good. So how I'm going to solve it? By looking back to our test, my test, and adding another asserting statement saying, okay, the square root of 0 is 0. Then I will rerun the test, and it will tell me, if I run the mutation testing again against that new test suite by adding this new assertion statement, you can see that the mutant has been killed, meaning that my test was able to detect that there is modification has been introduced in the code. And this is great. All right? So I showed you one example of how to create a mutant. And what I did in this example, I just changed the operator from smaller to smaller or equal. However, there are plenty of types, and Olivier is going to tell us about those types of mutations.
Okay. There are different types of mutations. There's three main ones. Value mutations. For example, you have a constant, we just change the value. So in your code, you have I equal 0. And the mutant would just be to change I to 10, for example. So we change a small int to a big int, a string to an empty string. This is a value mutation. It's a very basic one. Then there is some decision mutation that are more advanced. So in your code, we're going to change entire blocks like if and else, or allocation equal becomes equal plus, or if else become just if. And then the last one is statement mutation. This is even more advanced. So we're going to change entire functions. So a function can become like an empty function, or the return value is going to change. So we're going to change entire statement in your functions. So if I take like very few examples, we have the arithmetic operators, plus become minus, times become divided. This is changed in your code. Array become empty array. We just change the values in the array. Assignment expression, I mentioned plus equal becomes minus equal. Very basic. Then block statements. We have this say something method that just becomes an empty method. This is going to be changed in your code, and then rerun the test as Maha mentioned. What else? Boolean, true becomes false. And then you have plenty others. Conditional expressions, equality operators, logical ones, string literals, object literals, optional chainings. And depending on your language, you don't have access to all these mutants. Like optional chaining doesn't exist in every language, so it also depends on your language. So you have plenty of those. Just to show you a few other interesting parts. In some languages, you have these built-in functions, like to uppercase. And there is some framework that allow you to change these functions. So to lowercase is going to become to uppercase. Some is going to be replaced by every. So there's a bit of intelligence here. Another one I like is regex. I mean, I hate writing regex. And so, I mean, testing regex is something that is nearly impossible. But we're going to change some regex in your code and then run the test. That's pretty funny, actually. And so at some point you may say, okay, so what you're telling me is that I spent months writing my code and writing my test, and now you're telling me I need to write my code like 100 times to change every single line of my code from plus to minus and everything. Well, no, hopefully. Don't worry. Don't worry, there is some tool for that. So people have thought about it. So there is some tools that are going to use your code and change everything in your code. And they're going to create thousands of mutants for you and then run your test. So you don't have to create the mutants by yourself. And these tools, they give you what we call a mutation score. And the mutation score, just to make it easy, it's a bit more complex than that, but if I want to make it easy, it's the number of mutants killed divided by the total number of mutants. As Maha said, we want to kill the mutants. There is a bit more behind this when you have some mutation timeout because like a while loop become like while true, for example. But basically, that is it, the mutation score. And the mutants only test your test. So if you don't have 100% test coverage, you can still have 100% mutation score. Like for example, very easy, if you follow here, I have 4 mutants created, so 4 lines in my code, or 4 things in my code that have been created, changed. 2 of them have been killed, 2 of them survived, so I get a mutation score of 50%, very easy. And what I want to achieve is getting 100% mutation score. Okay, demo time. If you didn't follow or didn't understand everything, I hope it's gonna get more clear with the demo from Maha.
Yes, so.
We have demo in, so Python, who is doing Java? Yeah, JavaScript?
Oh.
Okay. Good.
Okay,
That's why we
great.
have several demo.
Yeah. Okay. So let's start with the Python demo. So for Python, there are several tools that we can use. I use for this one today the MutePy. I noticed that the last version was 2019, and probably the community starts being active again. So the installation, pretty straightforward. Pipe install MutePy, and you are ready to go. And the main command you need to run is using the Python script. What you need to pass the main two parameters, the target, which means your source code, and then the unit test. So this MutePy supporting is unit test. And of course, there are other parameters to show some kind of reports. It can be HTML, can be JSON, XML, and in color way. So I'm gonna go to my Python. Do you see well my, or I should increase the size, the font size probably? It's big enough? Oh, okay. So everyone sees well? Yeah, okay. Oh no, that's this one. So let me do it like this. A bit better? Okay. So the example I have, simple, it's calculator. And the main functionalities is the basic add, subtract, multiply, divide, square. All right, great. And I have tests for that, for each function, and I'm gonna run the test. So I'm gonna run my test, and seems everything is good, and all the tests are passing, great. I'm using this coverage tool to compute the code coverage for Python, and he's telling me, oh yeah, great, you have 100% code coverage. Wow, great. So this is a magical moment for every developer, right? When you see 100% code coverage on the screen. Yes, we did it. You feel proud. Okay, so I have already installed the tool, the MutePy, and I'm gonna give you just a small note here. So as you can see, I'm running it in Docker because it doesn't work directly in Mac, but it works on Linux perfectly fine. So it's the same command here as I showed you earlier, passing the target and the source with other parameters to show the mutants and to export a report. Okay, great. What he's telling me that I have this metric, which is the mutation score, it's only 64. Remember, I had 100% code coverage, and now mutation score only 64. And what he's telling me that he had like generated 14 mutants, which means 14 changed copy of my code, where there is only one change at the time. And he managed to kill only 9, which is good, but there are still 5 survived. And what I want, our goal, is to kill all of the generated mutant. So here he's telling me what he killed and what he generated. So as you can see, for example, if you he replaced this operator with this one, and the mutant survived. He replaced the multiplication with exponential, and the mutant survived. However, when he replaced this operation with another one, he managed to kill the mutant. So that's great, okay? Let's pick one and try to kill it. So for example, and as you can see, so it's not only operators. Here he changed a value, a static value. So instead of I'm comparing with 0, I'm comparing with 1. So he changed a value, all right? And the mutants survived. So let's try to kill this mutant. So this one for the divide function, okay? I'm gonna go to my test, the divide function, and here it is. So he's saying if I replace the 0 with 1, the mutant's gonna survive. What I'm gonna do, so I'm gonna add another statement, simply, to my test, and I'm gonna say, let's put this one. Okay, so the test, of course, will pass. And let's try to run. So previously we got 5 survived, and 64%. I'm going to rerun it again. Oops. And suppose that I managed to kill the one where he has changed the 0 with 1, and I increase the percentage of the mutant, the mutation score. So here he generates, so the same you need to do that to kill all the mutants, yes, because our goal is to kill them. So there are 14, we need to kill all of them. So what I want to show you that the report, I like this report, so it's this one. And as you can see, it's summarizing what has been done. So he's telling you what was your target, what's your test, and what's your score, what the time it took. And even he's showing you all those 14 mutants that he had generated and even giving you the type. Is it arithmetic operator replacement? Is it changing a static number? Is it adding a new statement, removing a new statement? So he's giving you. Even you can go to hear the details if you click and to see more what has been changed. So this is the first tool in Python. There is another one I already tested. What I noticed, it's a mute installation using pipe, really straightforward, and you see the commands to run it. The number of mutants has been not the same. So in the first one, MutePy, there were 14, here there were less. So, and there's configuration file where you can say what the percentage of mutant you want to generate. The last tool, which I recommend that people can use, because I saw that it's the community, they're really pretty active, and it works really like a black box for kind of PyTest, not only for unit tests, so that's perfect. And similarly to the other previous tools, installation super easy. Okay, so this is for the Python demo. Let's move for the Java demo. So in the Java demo, there is a tool that's really widely used. It's PyTest. And you can see here's the source. You can install it using Maven or Ant or Gradle, or you can run it using the command line directly. So for today, what I have used Maven, and so the installation, what you can do, I'm going to go to my IntelliJ. Okay, it's here. Sorry, I didn't see it. And I think the font also too small. Probably here. A bit better. Not really. So what I want to say, how you install it. So in your pom.xml file, in the tag build plugins, what you need to do to add this plugin? Basically, where you pass its PyTest, you pass the artifact ID, and you choose your version, okay? That's great. And so you are ready to go on to run. What this tool provides two goals. What I'm going to use, it's the first goal, which is mutation coverage goal, where you pass your mutation coverage. This is your goal, and you run it. There is another goal where you link, the goal is SCM, linking the code with the source control, version control system, meaning that you run the mutation only, this code analysis only when you have new files added to your repository or you modified files, okay? I choose to run this one today. So it's the same exact example. It's the calculator. I'm not going to go through it. So just I'm going to run the command. Of course, there is the variable where you want to enable the history if you don't want to if you want to really accelerate this analysis. So I'm going to run this goal, and let's see what we will get. Before showing this, actually, what I want to do, run the test, because I have the test. What can you see here that I have only 50% of code coverage, okay, in my test? And this is what Olivier mentioned. This is very important. You don't need to have 100% code coverage to be able to run mutation tests. It has nothing to do with that. So in the Python example, I showed you that I have 100% code coverage. In this example, I have only 50%, and I'm covering only 62% of my code lines, okay? So those two metrics, they have nothing to do with each other. You can run a mutation test regardless what the code coverage you have. Okay, back to my analysis using PyTest. So what it shows to me, actually, that there has been 10 mutants been created, but only 7% have been killed. So the mutation score here at this moment is 70%, and I want to kill all of them. If I go, it's not as fancy as the Python, so you can see, but it shows you what type. So it shows you that the mutants that have been created, they are from three types, different. One of them is the void method call. The other one is math. The last one is primitive returns meter. And it shows you for each type how many mutants they have been generated and how many they got killed. So for example, the first one, there were 2 generated and none of them got killed. So I need to dig deeply here to understand why they didn't get killed and try to improve my test suite. And so on and so forth for the other kind of mutants. What I like about this tool, if I go to the pom.xml file, actually in the configuration, you can add, so inside the plugin, there's configuration section. What you can specify the package, the classes you are targeting to create a mutant for them. What's also the target test you want to run against those mutants. And even more, you can say what kind of a mutant you want to generate. For example, I don't care about mutants about primitives or math. I care about something different completely. Here I care about the constructor calls, or I care about only void method calls. So you can specify that. That's what I like about it. Even you can also avoid creating mutants for lines of code where you have calls to specific functionality. For example, here, I don't want to create a mutant that's going to be mess where I have lines of code I call logging, because I don't care about it. So I can avoid this, so those mutants will not be created. So as you can see, it's really, you can configure the way you like and limit the number of mutants, check them one by one incrementally, and you can play with it the way you want. And of course, it generates kind of HTML, and not as fancy as the Python one, but still you can see the code percentage, code coverage, and the mutation metrics coverage as well. So I think that's all for the Python and the Java, and what we can go for is the JavaScript. And I let Olivier.
For the cooler kids in the room, let's go for JavaScript. Okay, JavaScript, I'm going to use a tool which is called Striker. So again, there's many tools you can use. Striker has been the one that apparently seems to be the most popular. Pretty easy to use. You just npm install the tool, and then you run it. So let's go to the tool. Okay, here it is. So just go on the website. There's a lot of things you can do. Striker, actually, if you check it, there's different versions. It works for JavaScript, .NET, even Scala, and it does a lot of things. You can integrate it with different CI/CD tools like GitLab, Azure DevOps, GitHub Action, everything. You can create mutants for you. You can, as Maha said for Java, you can do the same. Just say that I want only to create this value mutant, not statement mutants. You can do all that. Okay, let's go to the demo. Because I can't code. Okay, I'm going to try to steal code and do that. All right. What? Okay. No, I'm good. Thank you. Okay, here I have a file. So it's the same as Maha has. So I have this calculator. So a very easy program, nothing fancy. To add, subtract, multiply, divide, modulo. And I have my test. So I'm going to run my test here. Okay. And if I run my test, you will see that, as Maha had before, I had 88% of test coverage. So not all my tests have been tested, but I still want to see if the tests I wrote are good enough. So I'm gonna run Striker. Come on, right hand. I'm going to run striker, and what it's going to do is going to... What? npm run, that's better. And so it's going to create mutants for me, and then it's going to write the test after for me. So you can see all the mutants it has been created. So you see here, it replaced this whole statement by just an empty statement. Here it replaces a less than 0, it replaces it by false, a less than 0, less or equal to 0. And in the end, I have a mutation score of 77 because it killed 14 mutants, but some of them survived. So it shows me that in some of these functions, not everything works. And it also gives me this report. If I go back to Chrome here, I have a mutation report, so you can see that 77% of my is my mutation score. You can see all the killed mutants. So this one, for example, it replaced minus by plus, but I don't want to see the one that killed. I want to see the one that survived. And here I have not covered, we don't care. I have 2 that failed. So the one that replaces less than 0 by false means that I don't test everything on my code. So if I go here, it means that I have a test missing. So I go to my test, I'm just going to add a new test. So I'm going to also test the square root of 0. And by doing that, I just add a new test. And if you go check my mutation now, I only have 1 that survived. So it means I killed another mutant, but I still have 1 that survived. And the one that survived is when I replace a less than 0 by false. And it's because I don't actually test the error here. So I'm going to add a new test when I do like a square root of -1, because that's not something that I had tested before, when I have a minus, like a negative number. And I run it again, and then you can see that now everything works. And if I go back to the page before, you can see I have a 100% test mutation score, even though I don't have 100% test coverage. So again, as Maha mentioned, mutation score can be 100% because it tests your test. So if your test doesn't cover 100% of your code, you can still have a mutation score of 100%. Now, this is for a very small project. Here I have a quite bigger project, which is just, can I just start it? Oh, I think it's already started, okay. So this is just a very basic application to order things. So I say I want like 1 Coca-Cola and 2 beer. You can submit an order. You need to get your age because there is alcohol. And then you can just, place order. So very basic application though, but there is like way more files to it. And so if I go back here, and I'm going to run, so it's an Angular application, by the way, and you can see that there is way more source files. So I'm going to run the test, still, here, and you can see that in this case, I have 100% test coverage. So normally, all my test has been run at least, my code has been run at least 1 by my test. But then if I run Striker, I'm going to copy paste because right hand, npm run, and there I'm going to run Striker, and you can see that. So it's creating a lot of mutants, so it takes way more time. It's going to create 159 mutants this time. So a lot of changes in my code. And here you can see that my mutation score is totally different. And actually, if I go to the report here, no, it's not. Come on, click. Oh, I just want to open the file.
Copy paste.
Okay, so here's my file. So you can see that the total mutation score is like 57%, so not very good, even though I had 100% test coverage. And you can go see for every source file. So I go to this one, I can see that 21 mutants have been created but have survived. And you can see all of them, like for the total price, for example, you just empty the function. For this one also, but you have also all these changes. It returns undefined, it returns true. So all these mutants have been created but haven't been killed. It means your tests are not sufficient to test your software. So that is for mutation in JavaScript. All right, you take it back.
Yes. All right. So we have shown you, three different demos for each programming language: Python, Java, and JavaScript. And in those three demos, we have shown you that sometimes I have code coverage 100%, but the mutation score was less than that, and the other way around. What we wanted to say is, again, so we have a metric called code coverage. It's great, and when you reach 100%, it's a magical moment, as I mentioned earlier. But this metric is not enough. It's not enough, and that's why the mutation testing has been introduced, to test the test. Why we care about that? Because the unit test, or the test, what we have today, it's our first source of truth to tell if our code is working as supposed to do, and it doesn't really hide some edge cases not covered there, okay, or corner cases. And that's why we care about improving the quality of our tests. And having those two metrics is very good, but one of them, having like only code coverage, is not enough to tell that our code is working as supposed to do and our test suite is sufficient. And insisting on the fact, like having 100 code coverage, you might have it, but you might get stuck at 99% mutation score, and you keep telling yourself, no, I'm gonna reach also 100% mutation score. Well, that's fine, because there are cases you might never reach the 100% mutation score. And why is that? Actually, because there is a special kind of mutants, what we call them equivalent mutants. What those mutants? So those also change in the code, but this change doesn't change actually the logic of our original code. That's why those cannot get killed. And it's fine. That's why you can't have 100% mutation score. Let's have an example of those equivalent mutants. So again, in Python, if we have this function where I want actually to implement a method where I get an URL, then using this URL, I will go to the web, fetch the web page, and bring it back. So kind of optimization, I decided, okay, I will implement dictionary, where the first time I fetch the web page, I will save it for the next time that I don't go again to the web page. So I have this dictionary, the key is the URL, and the value is this web page. So first time I will do that, second time I will not go to the web because it's already stored there. Then a mutant for this piece of code will be, because we said that there are different kinds of mutants, can be really removing this block of code, this where I have the if close statement, okay? So removing this, actually the logic of the program didn't change at all. And if I run my test, actually it will pass, and there will not be like any detect of change, because this doesn't change. The program is still working and the test is still working. So this kind of a mutant cannot be killed, and this is what we call equivalent to mutant. Okay, great. So we showed you a lot of advantages of using mutation testing, and it seems, wow, great. Well, actually nothing perfect in life, so it has some limitation. So what we need to keep in mind that it can be time consuming, and as you have seen, we showed you only simple examples like using the calculator, and there are like more than 10 mutants can be created for this main functionality in calculators, okay? So it can be really overwhelming for developers to do that, and thanks for those tools, they can generate those mutants for us. So large number of mutants can be created, but there are tools that they help us to really limit what kind of methods we want to mutate. And as I showed you in the PyTest for the Java demo, that you can say what you want to mutate or not. And you might here ask yourself a question, like, how can I run mutation testing at scale? And can you imagine, like, if you have really big project, and here Google, what they have done, actually, they are using mutation testing, and at Google, in this practical study, they show how can they implement mutation testing at scale, and more precisely at their code base, which is 2 billion lines of code where they run around 150 million of tests on daily basis. Can you imagine for this 2 billion lines of code with 150 millions of tests running on daily, how many mutants can be generated? It's a huge, right? It's a crazy. So what they propose in this study that what they will do, they will run the mutation testing incrementally, meaning that at the level of any pull request, they can run the mutation testing. They will limit the number of mutants created by each line of code, by each operation, by each code review. They will filter out all those mutants they look to the developers are irrelevant based on some historic performance of those mutants, and so on. So using those recommendations, they were able to run this mutation testing on their code bases.
Yeah, if Google is doing it, you can't say that your code is too big to do mutation testing. That's not an excuse.
Great, yes, completely. 2 billion. Last but not least, one of the limitations of this concept, this technique, it's you can't apply it as a black box. Why? Because you always need the source code of your application to be able to modify it. So it cannot work as white box, as black box. As takeaway, as I said, and again, so code coverage is great, but it's not enough. And having another metric to evaluate the effectiveness of our test, testing the test is good. And those tools, mutation testing tools, they provide another metric, which is the mutation score, can help us really to tell if our test suite is efficient or not. What we care about, why all this speech? It's because we care about the quality rather than quantity. We know, all of us, that I can fake the percentage of the code coverage by writing faked and bad tests. So that's easy to do. That's why we care about quality, not the quantity. And of course, automation is very important because we can do that manually, creating our mutant by hand. That's crazy. And sometimes we need to accept that 100% mutation score cannot be achievable, so that's fine. So what we showed you for Java, Python, JavaScript, but for the other tools, also if you are interested, there are mutation tools, mutation testing tools for C, C++, PHP, Ruby, Golang, Swift. So there are plenty, Rust, there are plenty of those tools. You can look at them and install them based on what you prefer. And you can find our slide at slides.com/my name. And I hope that you really learned something with us today. As you have seen with us, it's really pretty easy to install it, just you need to run it. So I hope that all of you go back home or you share it with your colleagues, with your friends, try just to install it on what you have today, any project, and see what mutation score you can get. And you can share it with us. Thank you.
You need to have tests first, right?
Yeah, yeah, of course. If there is no test, there will be like mutation score 0. All right, thank you so much, everyone. I hope that you enjoyed.
Is there any question?
You learned something.
Yes. I mean, the thing is, all the tools we showed you, I don't think any of these is maintained by the language owner. They're all done by community or companies. So you just have to check online if someone has done one for Dart.
Other questions?
Yes.
I can start. So the goal is really what you want to improve. You want to improve the test itself. So what you can look at it as a mutation test, it's testing the test. So why we care about that? Why you care about improving your test? Because your test actually, as we explained at the beginning, it's your source of truth to tell if your code is really working well or not. So if you can look at it, so you have your code, your source code, you have the test, they have the mutation test. So if I improve this one will tell me to improve this one indirectly. So like this indirectly, you know, but the goal is to improve the test. Mutation test has nothing to do with the original code, but it's improving the test itself. It's testing the test, simply. Exactly. Yeah, testing the test.
Yeah, next year we come back and we show you how to test the mutation test, to test the code.
This is for artificial intelligence, not us.
Yes.
Exactly.
Absolutely.
Exactly. This is the whole point. Exactly. That's what I was saying. You have the mutation test, you have the test. But the test is improving the code. So if you improve this one, might help you to identify some hidden cases, bugs in the original code.
Yeah, the goal is not to identify useless tests. So yeah, if you add no new tests, you may find some bug in your code. Absolutely. Thank you. Yeah, we saw it at some point. There was also at some point just changes by like if a less than 0, it just can say if false. So I can change the entire structure. I can even sometimes remove the else in an if else. So I will show there's like these value statement condition, different kind of tests of mutants, sorry, and they become more complex. So yeah, it's not only changing signs, even though it's usually the kind of thing you miss when you write your test. It's all the edge cases, like when it's 0, when it's infinite, when it's just -1 and not positive. So that usually the useful one, but no, you can have more advanced changes. But every tool manage mutants differently. So some tools are going to generate like 100 mutants. You change the tool, it's going to generate like 50 mutants. So it depends on the tool, and also the tools are going to generate always the same mutants. Otherwise, you may break everything when you run it in your CI/CD. So, but you can run different tools. So it's going to generate different mutants.
Yeah.
Very good. Thank you very much, and enjoy the rest of the conference.
Yeah. Thank you so much.